So today, just very quickly, we will finish with the evolution equation for the shift, and then we'll move on to do some simulations. So the shift conditions won't take long, and I don't think that I will need the 2 full hours today, so hopefully the fact that I was a bit late will not impact the what we're going to see today. Okay, so in the previous lecture we saw that the gauge conditions for the labs which we ended up settling for this 1 plus log slicing, basically related to the ensuring that the volume elements seen by the observers never shrunk to 0 size. So in that way one avoided certain singularities. Okay, and we saw that this 1 plus log slicing is such that the slices that the lapse goes to 0 inside the apparent horizon, so time freezes, coordinate time evolution freezes inside black holes in this slicing, and those slices are pinned at some finite distance from the physical singularities. So in this way these slices avoid the singularities. So now we have to find conditions for the shift. So those conditions, so if the conditions for the labs are motivated by ensuring that the volume elements seen by the observers remain finite, the gauge conditions for the shift are motivated by ensuring that those volumes elements are not very much deformed. So to minimize the deformation of the volume elements. And the rationale behind this is that, of course, if your coordinates are such that the local volume elements seen by observers are highly deformed, this will imply that you'll have necessarily large gradients. And large gradients are always bad numerically, right? Because the larger the gradient, the more resolution you need to resolve it. Or if you have finer resolution, as in any practical simulation, then the larger the numerical errors you will have in that region. Okay, so we want to find conditions that minimize the deformation in the special slices. Right? So the deformation of the special slices is, the deformation is measured by the so-called shear tensor, which is the Lie derivative along the d by dt vector of the special metric on the hypersurfaces. So the reason why we use the time coordinate is because, again, even though GR is coordinate invariant, we pick a notion of time, and that's t. So we want to make sure that the deformations are as small as possible with respect to our coordinate time evolution. So those deformations are measured, one can show that they're measured by the shear tensor, and one can say, well, we want to minimize these deformations, so one can minimize this quantity, this positive definite. That's a variational problem. So minimization of this object, one can show that this corresponds, this gives this equation. Okay, and when you write this out, then this gives an elliptic equation for the shift of this form. Okay, so that's an elliptic equation for the shift. And again, I argued that whilst this is an equation that in principle would achieve our goal, in practice we do not implement it because solving elliptic equations is expensive. Okay? So the idea here will be, just as we did for the labs, is to come up with a hyperbolic equation for the shift that basically leads to solutions, or it's close to solutions of this equation. So in order to proceed, one realizes that this object, the shear, measures the deformation of the volume elements, but it also includes not just changes in shape, but also changes in size. But the changes in size of the volume elements are somewhat taken care of by the equation for the lapse, right? So we want to now, instead of considering the shear, we will look at the traceless part of the shear, which only takes care of the deformations, but keeps the volume, the size of the volume fixed. So we will look for another object, which is, as I said, the traceless part of the shear. Okay, because this captures the changes in the shape, but the volume is the same. So one then minimize minimizes this object, which again gives rise to an equation of this form. Okay, and one can see that this equation is basically the same is equivalent to this equation. Okay, just the divergence of the time derivative of the conformally rescaled metric. I'm not going to prove it, but this follows from this. This is the same. Okay? And you can then write it explicitly, and you can see that this, if you now use the evolution equation, so one of the BSSN equations was the evolution equation for the conformal metric, and if you substitute that equation into here, then that will give elliptic equation for the shift, which is very similar to the previous one. So it turns out that this equation is okay, so it's very similar to the previous equation. It's just that now we have the traceless part of the eccentric curvature on the right hand side and some factor of the lapse. So it turns out that, again, ultimately what we care about is the highest derivative terms, right? That's what affects the principal part. And when it comes to solving elliptic equations, then what determines that an equation is elliptic are the highest derivative terms. Okay, that's also true in elliptic equations. So this equation is very similar to an equation, to this equation. Okay, one could choose to impose this equation instead, and I'll write it out in a second. And it turns out that this is an equation that Dirac himself proposed when he was studying radiation gauge as the analogous of radiation gauge in general relativity. So it came from a completely different context. But the advantage of this is that now these are just partial derivatives, so you can just commute these partial derivatives, and this gives this. And if you now remember, I don't need this anymore. When we implemented the BSSN equations, when we discussed the BSSN formulation of general relativity, we defined a new variable which was this gamma tilde, which was basically the minus the derivative of the inverse conformal metric, right? So this equation basically is equivalent to this, to setting to 0 the time derivative of this variable. Okay, and that implies, if you write it out, so instead of having the covariant derivative, and you don't have this volume factor here, but that's very similar to the condition that we just wrote. So this is simply to show that this condition, you can write it in a covariant form, and again, what you see is that the highest derivative terms are the same as in the previous equations. So somehow, this condition is morally, or is close enough to the condition that explicitly imposes the minimization of the changes in shape of the volume elements. So what we are going to do is, well, this is much simpler, okay? And again, this is an elliptic equation for the shift, so that's expensive. So now what people did is to just come up with a hyperbolic equation that essentially evolves towards this condition. And hyperbolic equations, as we said, are much cheaper in terms of memory requirements. Okay? So the hyperbolic version of this is what's known as the gamma driver. And that's the other gauge condition that's used in numerical relativity. Okay? So what we're going to do, a hyperbolic version would be something of this form. We want a second order equation so one can show that in a certain limit, solutions to this equation would correspond to solutions to this. Right, so for example, one way to heuristically see this is that if the shift settles is as you'd expect in a solution to an elliptic equation, then the time derivatives of the shift are 0, which then implies that the time derivative of this guy goes to 0. So in other words, or said differently, this translates it into an elliptic equation for the shift. So if this is satisfied, then this tells you that the time derivative of the shift is 0. So these are just free parameters that one can choose. Again, the choice of these parameters is completely free because these are gauge variables, so they can do whatever you like. And this parameter sigma, sorry, this parameter xi here is related to the speed of propagation of the gauge mode, and later we'll specify a value which will then ensure that those modes propagate at the speed of light in the regions far away from black holes. And this is a damping term. So this is a damping term, it's like a friction term in the equation, and what this does is to sort of keep the oscillations of the shift under control. So typically this is a parameter that one fixes and is proportional to the inverse of the total mass of the system. Okay, but this is a damping term. So basically, one then in practice, once you get this equation, we have to make a reduction, a first order reduction in time. So we write it as a first order equation. And in practice, what one ends up using are this set of first order equations. Okay? Okay, this is just the advection derivative, and the reason why you, instead of just having a time derivative, you add this advection term is because then the light cones that these variables C are just the same as the light cones of the rest of the variables. So that helps with stability. And for psi 3/4, then you can show that then these gauge modes propagate at the speed of light. But in other circumstances, it may be advantageous to choose different values of this parameter. For example, in high dimensions, you have to free them. So the point I'm trying to make is that you're completely free to play with these parameters, and sometimes you have to do so to achieve numerical stability. Okay, but you don't have to do any fine-tuning. So you can always find open sets of parameters for which this works. And these equations, you have to, when you analyze the hyperbolicity of the system, you need to include these two equations together with the 1 plus log slicing condition for the labs, together with the BSSN equations. And then one can show that that system is strongly hyperbolic. And this is the BSSN formulation of general relativity in puncture gauge. Again, you are free to include these advection terms, and in some codes, there's always a parameter that allows you to turn them off if you want. In some cases, you can turn them off and it works fine. So they're not critical. Okay, so that's all I wanted to say about BSSN. So now I think we could move on to the simulations. Maybe we need a projector. Once we set this up, are there any questions about BSSN and the gauge conditions?
Are there other choices of gauge that are used much, or this kind of?
They are basically the two choices, which is harmonic coordinates with excision, or this. I'm not aware of any other choices that are used. And it's one of these things that it doesn't mean that they don't exist. It's just that when people found this and they found that they worked for the problems that they were interested in, like black hole binaries, that was the problem, or neutron star binary mergers, then people just stopped looking to this. Okay, this works, then we're done. We can move on. So it's something that probably since the mid-2000s there's not been any investigation on alternative gauge conditions.
But you can imagine it's another problem.
Yeah. So
there might be a better, more appropriate.
Yeah, absolutely. There's no reason why this is the only choice, by no means. And in fact, as I said, in high dimensions, one has to play with these parameters. There's instances in which, so basically this is a damping term for the shift, and it means that the shift is, you restrict the oscillations of the shift on a certain time scale, which depends on the time scale of your system, and if you have black holes, that's the mass. But in situations where you have different length scales, for instance, when you have an extreme mass ratio, where one of the black holes is much smaller than the other one, then each black hole evolves on its own time scale, then you have to come up with modifications of this gauge to account for the fact that you've got two time scales that you need to resolve. But they're only, I would say, they're just variations of this. Yeah. But it's a slightly different version of BSSN from the one that we saw, and the difference is almost trivial. But it turns out to be useful when you use, so for example, spherical polar coordinate. So because some of the relations that I stated are only true in Cartesian coordinates, right? Because remember, the point is that one of the issues is that this quantity, which is defined as the contracted Christoffels, this is not a tensor. So that can be an issue sometimes, for example, when it comes to imposing boundary conditions. But also this equality is only true if this metric has determinant 1. And again, you can think of situations where this is not the case. So for instance, even if you do asymptotically flat spaces in spherical coordinates, then the determinant of the metric is not 1, right? It just depends on the radius and the sphere. And if you want to do simulation, say in other spacetimes like de Sitter or anti-de Sitter, then it's useful to introduce a background so that you subtract the background. So for that reason, one can generalize the formulation of BSSN that I presented in a way such that it's covariant. And that's what this paper does, and that's what I implemented, because we want to do a simulation in spherical symmetry. So of course in spherical symmetry it's advisable to work in spherical coordinates, because then you have to solve essentially, in this case, PDEs, like 1+1. But the issue is that in general relativity, as you know, there's no dynamics in spherical symmetry by Birchhoff's theorem, so you need to introduce matter. So we'll do a simulation of a black hole with a scalar field, just because we need the dynamics from the scalar field in spherical symmetry. But it is completely general. So the idea is the following. So I'll just go through the main point of the paper. Does this have a pointer? No. So one defines the conformal metric in the same way, but one of the things that you can do now is to simply do not. Okay. So one of the things that you can do is to then not impose that the determinant of this metric is equal to 1, but it's equal to the determinant of a background metric, and it's constant during the evolution. That's one thing that we can do. And the second thing that you can do is to introduce a background metric, which this is always, so let me just explain. So basically the idea, the things that you can do to make it covariant is first, as I said, don't fix the determinant, just leave the determinant of the conformally rescaled metric to be the same as the determinant of a reference metric, which in our case is going to be Minkowski space in spherical coordinates, but it could be ADS or it could be DS, in whichever coordinate you like. That's thing number one. And the second thing that we're going to do is we want to define these variables with a vector, but now we want this to be a true vector, right? And the way you do it is if you have the conformally rescaled metric acting on the difference between two connections. Okay, now this transforms as a proper vector. So we'll, instead of using, so before we forgot about this part, and which is true if you use Cartesian coordinates. Okay, then that's all the Christoffels vanish, right? But in spherical coordinates they are not. So we're going to work with this quantity, and then what you do, then you can write down all the BSSN equations in terms of covariant derivatives instead of like partial derivatives. So everything transforms as a tensor. Okay, that's good enough. Okay, so we first define the variables as we did before. We do the usual rescaling. Now, so this is, you can see that this is the ratio of the two determinants. Then you do the same rescaling with this quantity. That's the traceless part of the extrinsic curvature. And then we consider the difference between Christoffels. That's the Christoffel of the rescale of the conformally rescaled metric, and this is going to be the Christoffel of a reference metric. And then we contract them, just as I showed there. And now this is a proper vector. Okay? So now we will have this constraint. So we'll introduce a new variable, which must be equal to the contraction of the difference between Christoffels. And if you do that, then we, just as we did before, the determinant of the conformally rescaled metric doesn't evolve. So before we had that this determinant was set to 1, so now it will be just a function, and whatever the determinant of the background metric is. And then if you do that, then you can write down the BSSN equations in these forms, where now they are manifestly covariant. Okay, they are the same as the same equations as we had before. Now the only difference is that now in here they're written explicitly. So remember that when you do conformal rescaling, you can write the Ricci as the Ricci of the conformally rescaled metric, and another term that depends on derivatives of the conformal factor. Right? So here they've just written things out explicitly. So that's the Ricci of the rescaled metric. And then, as we had before, that's the evolution of the new variable, and these are the covariant derivatives with respect to the reference metric. Okay, which in our case will be flat space in spherical coordinates. So we're going to solve this system. And yeah, so we're going to solve this system. And then since we have to compute these covariant derivatives with respect, so again, in the computation of the Ricci, you can write it as these in terms of these covariant derivatives of the reference metric, and then you get an extra term which is like some contracted Riemann of the reference metric, which has not been included here because our reference metric is going to be in Minkowski space. So that Riemann that piece doesn't contribute. But if you were to do this in ADS or DS, then you would have an extra piece here and here as well. So that's the choice of reference metric. Okay, we choose our reference metric to be just a flat metric in spherical coordinates, and because we're going to do the simulations in spherical symmetry, then without loss of generality, we will also fix the angle theta to be pi by 2. Okay, you will see this in the code. Now, because we have to compute these covariant derivatives, then you need the exclusive Christoffels, and because here you see we've got two covariant derivatives of the metric, then it's practical to write the metric in terms of the reference metric plus another perturbation, if you want, but this need not be small, right? So here we're going to solve the fully nonlinear system, so this perturbation is not small. But of course, this makes the computation of these covariant derivatives that appear here very straightforward, right? Because those covariant derivatives kill the covariant derivatives of the reference metric. Now the last thing that one needs to do when you work in spherical coordinates is to make sure that the quantities are suitably regular at the origin, right? Because in spherical coordinates the origin is singular, so you need to impose suitable regularity boundary conditions there, and we will do that. So it's useful to just pull out suitable powers of the radial coordinate, and then at r equals 0, then all these quantities are parity symmetric. And then you do the same with respect to the poles at theta equals 0 and theta equals pi by pi, but this will not be an issue for us because we work at pi by 2. So there's nothing to care about. Okay? So these powers of r here are just there to ensure, as I said, that these variables, that these unknowns, the h's, are suitably regular. And likewise for the vector, you just pull out the powers of r, and so on. Okay? And then in the code one pre-computes all these quantities. And the reason is that when you do numerics, in order to increase the accuracy of the code, it's always advisable to do as many computations analytically as you can. Right? So if you've got here like a variable which is defined as, say, r times this unknown, then you don't want to compute a numerical derivative of this quantity. You want to compute, when you take an r derivative, you want to take the analytic part out and then do only the numerical computations that are needed. Right? So that's why here they pre-compute the covariant derivatives in this way. And that's what we do in the code, right? Yeah, and in the code you will see that we work with rescale quantities, so which is again when you can make contractions, there are powers of r. So you don't want to numerically compute a quantity which has like a power of r in the numerator and a power of r in the denominator, so they cancel out. So you want to do these cancellations analytically. This improves accuracy. Okay, so this is the system that we are going to solve. This. Okay. So now I'm going to show you the code. I just ran it before coming here, so just to make sure that it didn't crash, it didn't do anything that would make me embarrassed or anything.
So it's definitely crashing, right?
So it's not going to crash. So let me just, so to show that it works, then we'll start from scratch. I checked that it works, so. Okay. So let me guide you through the code, and I'll send this code to Damian and the others so that you can have a look at some later if you want. I should say that this is a mathematical version of a code that a colleague of mine, Katie Clough, wrote in Python, and which is already publicly available in the GR Chombo website. So I basically translated it into Mathematica because I thought that for this audience, people would have more familiarity with Mathematica than with Python. But know that there is a Python version of it which is faster. But I hope that this is clear enough. Okay, so here, let me guide you first.
Sorry, can you make
Yes.
the font bigger?
Bigger, sure. Like this?
Yes.
Is everyone okay? Or you want it bigger still?
Maybe. Yes, it's good. Thank you.
Okay. All right. So first of all, so the way we do the computation, we will group all the variables into a single vector. So then you split this vector into chunks. So that, say, each variable takes a certain portion of this vector. Okay, so we first name our variables, and we order them in this way. So we order them in this way. So we've got 12 variables in total, which are these u and v are the scalar field and its time derivative. So we do a first order reduction of the equation for the scalar field. And then these are all the BSSN variables. The h's, which are the rescaled metric, trace of extrinsic curvature, rescaled traceless parts of extrinsic curvature, but because it's in spherical symmetry, we only have the diagonal component. Okay? And then this vector, lambda, will only have a r component. Again, that's only true in spherical symmetry. And then we have the lapse. Well, we have the shift, the b variable that we introduced today, again rescaled, that's why it's little b, and the lapse. Okay? And we index the variables, and this will then is useful to then access the chunk of the vector that corresponds to that variable. That's just for making it easier to manipulate. And then at r equals r naught, then we want to impose suitable regularity boundary conditions, and with those rescalings, the variables that do not have indices along the r direction are all parity symmetric, whilst the vectors with index r are all they should change sign. Okay, that's just regularity. And then at large distances, this is in flat space. So each of these variables, you know what boundary condition should satisfy because you impose that they decay such that the spacetime is asymptotically flat. So the decay has to be sufficiently fast, but not too fast. And if it's not fast enough, then you would spoil asymptotic flatness. But in practice, in flat space, you basically get away with murder in the sense that you just place the outer boundary sufficiently far, and even if the boundary conditions are not right exactly, then you've got dissipation, numerical dissipation, and all of that takes care of these small errors that you are making by not imposing the exactly correct boundary conditions. You cannot do that in spaces such as ADS, where there is a boundary, where you have to specify boundary conditions, and you cannot get away with not doing it right. Okay, so that's not of a concern here. Okay, then in here we need to set up our grid. So we're going to use fourth order finite differences. So, and what we're going to do is we're going to have a grid that will extend from, so we're going to choose a grid. So if that's a real line, R, then we have some value R max, and here's the origin, 0. Okay, so with our grid, we're going to choose a cell-centered grid, and the only reason why we do that is because that's how we do it in GRChombo. So if you want to download the proper code, then you can do that, and ours is cell-centered. So that's why we have a cell-centered, you use cell-centering here as well. The reason why we do cell-centering is because when you do hydrodynamics, then by numerical methods for hydrodynamics are better if you use cell-centering to basically construct numerical weak solutions to capture shocks, basically. But in here, that we are solving classical equations, you could use node-centered grids, and that in fact will make it easier to impose boundary conditions. Okay? So our cells are going to be like this, and this is where our grid points lie. So there is no grid point at r equals 0. This turns out to be an advantage because r equals 0 is singular, so the equations will blow up there because of the coordinate singularity. So you don't want to evaluate your equations there, right? So we evaluate them at some finite distance. But then these cells that you have here, these are the ghost cells. So they're not part of our computational domain, but we fill them with data, the real data is here. And we fill them with data such that when you take derivatives, so when you use finite differences to compute the derivative here, you use information on both sides. So you need data here to take derivatives. You could do cited derivatives. That's something that some codes do. But then you need to implement different derivative operators depending on where you are on the grid. So it turns out to be easier to just have a single-centered operator, and then the price you pay is that you've got to have these ghost cells that you need to fill with data. And the way we fill with these cells with data is by imposing boundary conditions. So, for example, if you've got a variable that is parity symmetric with respect to r going to minus r, then once you've got data here, then the value of this cell here must be the same as the value cell here, and you get the value here from the value there, and so on and so forth. And if it's parity anti-symmetric, then you change sign. And in this way you can take derivatives consistently. So the way the code works is you evolve the cells which are within the domain, and then after you've done that, then you fill the cells, the ghost cells, so that then you can take derivatives when you step forward. Okay? So these are the ghost cells, and the same here. So here so our domain goes all the way here, and then here we'll have 3 ghost cells that we will fill such that the functions behave in the right way near these boundaries. So in fact, you will see that we've got implemented 2 different kinds of grids. One is just a standard grid, which is equally spaced everywhere. That is fine, but then, in this case, because there's a black hole, so you've got more stuff going on near the origin, then you need many more grid points just because you need to resolve what's going on near the horizon. So here we also implemented a logarithmic grid, which is also finite differences, but there are more grid points near the origin, and fewer grid points over here. So for the logarithmic grid, we didn't implement the right boundary conditions at infinity. We just copy data from here. So we do something which is quite dirty, but it works, kind of. Again, if you wanted to produce accurate waveforms, then you don't get away with these dirty tricks. You have to do it the right thing, right? But that's not what we do here.
Why that 3?
3, because the order of the differences then if you want to have fourth order differences, then for the first derivatives, you need 2 points, so you need only 2. But then we also you have these advection terms that force you to take sided derivatives, and for those you need, depending, you need 3, you need more. So if you use a lower order stencil, then you could get away with fewer Go cells. So that's something that one needs to consider, because the more Go cells, it means the more memory you need, because you need to store more data. Right? So the higher the order, the more Go cells you need, and that at some point can be a limiting factor.
How do you choose R?
Huh?
How do you choose R? How far should it be to consider it as infinity?
In reality, infinity is not very far. I don't know, if it's a black hole of mass 1, then if you choose R, again, for the purposes of the simulation, I think R is like 64, and it's okay. And you can see that it's not far enough because you see some stuff there. But in practical numerical simulations of, say, black hole binaries of, say, mass 1, then you do the extraction, the wave zone. You are already pretty much in the wave zone at R equals 200 m or 300 m. But typically you set the outer boundary of the domain at like 1,000 or so. So it's like so far away that, you know, not much happens there. That's why the further away you get it, the less strict you need to be with the boundary conditions, because then, you know, the gravitational field is like smaller than, and dissipation terms can take care of these errors. Okay, so that's the theory, and here you pre-compute some things that you use later, so that's something you normally do in numerics. So the things that you computed, you need to compute it only once, so then you store, because it's just a real number, so it doesn't take much memory. So these are just the coefficients in the derivative operator for the logarithmic grid, and basically what we do here is, because the grid is not equally spaced, then you use Lagrangian interpolation of fourth order, and then you evaluate it at the grid points, and that's basically these coefficients, that when you then construct this Lagrange interpolant of this order, and you evaluate it at each of the grid points, then that gives you these coefficients of the derivatives. That's how you get them. Yeah, so we've got a function here that will generate the grid. Okay, so we've got two options, that if R is logarithmic or if R is not logarithmic. So if R is not logarithmic, then we have just a uniform grid, and if it's not logarithmic, then R is not equally spaced. Then also there's a function here, which is this function, that loops through all the variables, and it imposes the boundary conditions at the origin. So based on the parity of the variable, then it will fill in the Go cells to ensure that the variable is parity symmetric or parity antisymmetric. Okay? And then we have the same function, we have a similar function that imposes the boundary conditions at infinity. So this function, what it will do, after we've updated all the variables, when we've taken a time step, it will fill in the Go cells such that you get the right decay at infinity. And this function, this loops through all the variables, and this is the function that actually does the filling of the Go cells. Okay. Okay, numerical differentiation. So I think it's probably easier we just go through the standard finite differences. The logarithmic one is just equivalent, it's just the coefficients are different and depend on which point you are in. So this takes a numerical derivative, and that's for the second derivative, which is centered at point I, then you need points both to the right and both to the left, and this is the stencil. Then for first derivatives, again, you need 2 points to the right and 2 points to the left. And then for the advection terms that you have in the equations, remember that you've got all these, in the BSSN equations, you've got all these terms like beta contracted with the partial derivatives of the acting on the variable. That's an advection term. And for that term, depending on the sign of beta, you need to use information either to the left or to the right. This is just to make sure that the information propagates in the right direction. Right? And this, if you want to keep the convergence order to be the same, then you need to take sided differences, and you need to take enough points. So you see here, for an advection for an advection derivative calculated at point I, it uses only 1 point to the right, but 3 points to the left, and that's why we need 3 go cells for these advection terms. And then finally, we also implement something called Kreis-Ohlliger dissipation. So Kreis-Ohlliger dissipation, what it does is it kills high frequency noise. So in any numerical simulation, because you are approximating the derivatives by these numerical derivatives, this generates errors. And you want to suppress the errors that are captured, say, by those wave numbers which are of the same order as the size of your cells. The reason is that by getting rid of those errors sort of makes sense because you're not resolving those distances very well anyway, right? So you just clean those high frequencies, right? Because ultimately this is what you're not resolving. Okay, and usually, as we also, when we studied well-posedness, the problems come from high frequency noise. So what you do is you add a dissipation term to the equations, like a higher order dissipation term. So the order of this dissipation term is correlated to the order of your differencing. So if you've got 5 fourth order conversions, you want to add a dissipative term which is of sufficiently high order such that it kills the high frequencies, but also it goes to 0 in the continuum limit. So you add it with a coefficient such that it converges to 0. So in this, if you have 4th order finite differences, then you need to add a 6th derivative term. Right? And you can show that this goes to 0 in the continuum limit, so it's only a numerical artifact. And what it does is to clean the solution and the high frequencies. And that's important for stability, in particular for nonlinear systems. Okay? And yeah, so log derivatives is just the same, but using a logarithmic grid. And you can see it's a bit more complicated, but what it does is to use the coefficients that we have pre-computed earlier. So it's nothing, otherwise it's the same. Otherwise it's exactly the same. It's just that the coefficients are different. And then we have a function here that basically just computes derivatives of all variables. So in the BSSN equation, so only certain variables appear with second derivatives. So this function will compute only the second derivative of those variables that enter with second derivatives in the equation. And likewise, this function computes derivatives and the first derivatives and also the advection terms. Okay? All right, so because we need, maybe we can go through this. What can I do? Let's run this first. So let me do the following. We'll continue going through the functions whilst the code runs, because then otherwise we can then have a solution. Okay, so let me just do that. And then run the code. And then we go through these sections as the code runs. Okay, so we set total mass to 1. We have 64 points along the direction, and infinity is at 48 units of the mass. So that's not very far, and you will see the effect of this. I will go through this soon, but well, I can just explain it now. So this function basically, once you set up your parameters of the grid, say how many points you want and where the maximum radius is, and whether you want to choose logarithmic derivatives or just ordinary derivatives, then this function will generate a grid, a radial grid. Then, because when computing derivatives, sometimes we have to divide by dr, so again, we just pre-compute these quantities once and for all. So we don't need to do this like thousands of times every time we want to advance forward. So this is the CFL factor, because when you evolve hyperbolic equations, so in order to get conversions, for hyperbolic equations, the size of the time steps has to be correlated to the size of the spatial differences. And the reason is because if you want to have convergence, so if you have, say, the solution at some time level, like say Tn plus 1, and that's a solution at Tn. So the grid points are at the same location. So the only thing that changes is this, dt. So if the light cone, if, let's say, this, so you want basically the solution on this, at this level to be causally connected to the solution at this level, right? So if the time step is too large, then if this is too large, then this level will not be causally connected to this level. And if you have that, then you cannot possibly have convergence. So that's why you have this linear relation, and you have to, in principle, for equations, you can choose what is the maximum value that gives you this causal connection. But in practice, what we do is you just make it small, like 0.5, 0.25, and then if it works, then you are fine. If the code crashes, then that's one of the first parameters that you change. So let's make the CFL factor a bit small and see if it works. Right? And if it's too large, then the code is not going to converge. And that's because then the level will not be causally connected to this. Okay? So here we choose it to be 0.25, which is pretty standard. And that's because we use here we use an explicit time stepping, like Runge-Kutta 4, which is a standard. But if you use an implicit, then you don't need to worry about this. But then if you do gravitational wave extraction, then the smaller the time steps, the higher the resolution that you have in frequencies. So that's another issue that you need to take into account. So it's not just how fast the simulation is going to run, but also how much resolution in time you need if you want to extract the frequencies accurately, which is something that for, say, gravitational waves you care about. Okay? So that's the CFL factor. So if you have a parabolic equation, then the relation is of this form. Because parabolic equations, you have one time derivative and two space derivatives. So then the power here changes. Right? So parabolic equations, you can see that the time steps have to be very small. But for hyperbolic equations, you have a linear relation. Okay. So now we generate initial data, which we'll go through, which is a black hole and some scalar field profile. Sorry, no, there's no scalar field here. I don't remember now. Anyway, so that's our initial data, and here we plot the initial data. Oh yes, there is a scalar field profile. Oh, sorry, that's the conformal factor. So in this case, the lapse is set to be 1 initially, and that's the vector lambda. So what we say, we prescribe initial data for a black hole, and from this we compute the lapse because, this function lambda, because this function lambda is basically that thing we have there. So if you know the initial metric, then you can use that relation to compute the initial lambda. Okay, that's how you get initial data for lambda. Then we check that the Hamiltonian constraint is satisfied initially. Okay, and then you see that it is satisfied except near the origin, which is, it kind of goes crazy, but this is okay because that's in a way close to the singularity. Even though there is no physical singularity, there is a coordinate singularity there. And coordinate singularities for computers are nearly as bad as physical singularities. Things blow up, and this is reflected here, right? But that's enough. That's okay because this is inside the horizon. I'll see if in the version of the code that I send to Damian, I can code up an apparent horizon finder, so you can see that there is a horizon here, and I haven't had time to do it. But I will try to do it before I send it to Damian. So, and now here we do the evolution. So we said the final time is like 24. That's half of 48. So there's no coincidence because we put the boundary at infinity. So we want to make sure that whatever naughty things we do there then do not affect our simulation, right? So in this case, in order to avoid boundary effects, then if you don't treat the boundary conditions well enough, then that puts a bound on the time of your simulation. Otherwise, the junk from the boundary will contaminate the region where you have your black holes, and you don't want that because that's unphysical. Okay, so then that's the damping factor that you have in the gamma driver for the shift that we saw, this parameter eta, and that's typically chosen to be 1/2 times the total mass of the space-time. But again, this is something you can play with, but it should be of that order. So in this case, it's exactly that. Okay, because the total mass of the black hole is 1, so this is 1/2. Okay, and here now we run the code, and now we go through the functions. So let me just make sure the first step works, and if it works, then we can just continue. It's not very, I mean, it's a mathematical code, so you cannot expect it to be fast. That's not the point. Yeah, okay, it works, good. Okay, so let's go now through the functions whilst we this compute. So here, these functions, tensor algebra, we use them to compute like tensorial quantities that appear in the BSSN equations. So first, we use the indexing of Mathematica, which indices start at 1. In Python, the first index is 0, like C or C++. Mathematica things start at 1. So the first index will correspond to the r coordinate. Second index is the theta, and the third index will be phi, the azimuthal angle. And we work in spherical symmetry, so theta is pi by 2, so sine theta and all of these are 1, 1, 2. So the way this was coded is because it should be relatively straightforward to then generalize this to a full, like 3 + 1 dimensional code in spherical coordinates. Okay, so at some point you will see that it's useful to create like placeholders for tensors of different ranks. So for like a vector, 2 tensor or 3 tensor, like a Christoffel, for example, because the point is that because in spherical symmetry, many tensors will have many components will be 0. So we only want to fill those components that are non-zero, right? But when you calculate the right-hand side, you've got all the contractions, so you need to have all entries have to have a number, right? Otherwise, the code will give you none or whatever. Okay, so here this function basically, as you can see, computes the Christoffel symbols in spherical coordinates, and as I said, we only compute the components that are non-zero. So in this other function, it says rescaled. So the reason is that, again, to optimize the computation, you want to cancel the powers of r that will appear when the Christoffels get contracted with a metric which has its own powers of r. So in this case, you just do that already. So that is just to simplify the computation. But so then, yeah, so yeah, this is just I don't think it's function. I don't remember now what it does. Yeah, so here you compute the determinant of the metric of rescaled. Again, you just ignore the factors. You deal with the factors of r, and here so you see here in this case, the metric is. Let me just go back here. The metric that we evolve is this. That's the total metric that enters in some of the equations, and we compute this as a reference metric plus the perturbation. And in spherical symmetry, the perturbation is only the diagonal terms, and those terms enter with factors of r squared. So this function, what it does is to basically compute the rescaled metric, taking into account the factors of r here and there. Here you compute the inverse metric, and yeah, this is for just computational ease to take care of these factors of r. Piece of trace. So this function, given the metric, as you can see, it computes a connection. Okay, and because we write our metric as the induced metric plus perturbation, the covariant derivatives with respect to the background just kill the reference metric. Okay, so that's, you compute the connection, and the rescale, again, you just take care of factors of that. So we also need, in the equations, we need to compute the Ricci. The Ricci, which is computed, we need to compute Ricci. Okay, because that appears in the right-hand side of the Einstein equations. So we compute Ricci, and yeah, so that's, you just compute it in the straightforward way. There's no secret, but actually I just code it up in two different ways, and because, you know, Mathematica, there are certain operations that Mathematica is more efficient at doing that if you write it in the right way. But it's just basically that formula written out explicitly. Again, rescaling, the same thing, and then here we also need to compute lambda. So we do that, for example, when you have initial data, okay? Yeah, so the lambda is what I call this, the difference. Yes, that's it, yes. And then here we need to compute these two derivatives of the metric. We need this for the Ricci. So this function computes this first. Okay, and then we uses this in the Ricci. So if you go back to Ricci, you see that it calls the lambda, right? So remember one point that we made here, the previous day when we considered well-posedness, is that in the computation of the Ricci, on the right-hand side, this is not computed from the Christoffels. This is the evolved variable. Okay, so we need this, and that's this is not computed from the derivative of the metric. This is computed from the evolution variable. We call it gamma. Here it's called lambda. Okay, so we need this term and we need this term. So this function, Ricci, calls lambda and gamma. Okay, and sorry, the derivative of lambda and the second derivatives of the metric, and then plugs it in the formula for the Ricci. So the rest are just contractions of Christoffels, which in here they are explicitly computed in terms of the metric. And that's okay, because when it comes to well-posedness, the only terms that affect the well-posedness are the highest derivative terms, which are these two. The other ones are lower derivative terms. So the fact that you use the true contracted Christoffels or the evolved variable in practice doesn't make a difference. Okay. Yes, so that's, yeah, so this again is to compute the derivative of the evolved variable. And the way it's done, as you can see, in order to compute the covariant derivatives, you need to compute the derivatives themselves with the Christoffels. And here what we do this computation, but we only compute the terms that are non-zero in spherical symmetry. Right? In the fully 3+1 code, you just compute everything. But here, to make the computation faster, then we only compute what we need. And the same thing. Okay. So here we set up initial conditions for a black hole. This is called, if I'm not mistaken, that's Bowen-York initial data, which is just a black hole. Okay. So the RR component of the induced on the special metric has this form, and the black hole is there is, you know, when we did maybe I didn't emphasize this enough, when we did the evolution of the labs, when we do the evolution of the labs, basically, if you've all seen maximally standard Schwarzschild, right? So when we do, so if you take maximally extended Schwarzschild in this way, and you start with a slice like so, that's, for example, if you use isotropic coordinates, that's the slice, okay? So this 1 plus log evolution, what it does you can see that as you move forward in time, so again, you do this for Schwarzschild, this would be just change of coordinates, a time-dependent change of coordinates, but you not change anything in the space-time. So if you do this one-plus log slicing evolution for Schwarzschild, then you can see that the slices evolve like this. So, and then eventually they get pinned here. They avoid the singularity. So all these slices will accumulate at this point whilst avoiding the singularity. Okay, they really avoid the singularity. So they all pile up here. That's what it means for time to freeze inside the event horizon. But then outside, those slices will continue to get close and to somewhat get closer and closer to null infinity. But they, of course, they never reach null infinity because those slices are always pinned at space-like infinity. Okay, so this point here is like time-like infinity on this side of the Schwarzschild solution, and that's what this r equals 0 is. So that's that point there. So that's an asymptotic end of the space-time. So it's a singularity, but a coordinate singularity. It's not a physical singularity. So this is this initial data that we choose for the space-time, and from this you compute the conformal factor. Okay, so you populate the variable phi. You can see that you populate the variable phi, this index phi, whatever it is, we populate with the computation of phi that we have from this spatial metric. Then we set the lapse to 1. Where is the lapse? Lapse equals 1. Okay, so we will see a non-trivial evolution of the lapse. And then we compute the induced metric accordingly, once you know the conformal factor. Then once we know the metric, we can compute this function lambda, right, by just the Christoffels. So we compute this explicitly, and that's it. So I think in this case we don't have scalar field. These are another set of boundary conditions where you have no black hole but a non-trivial scalar field. And yeah, so it's the same thing. It's just in this case, I think in this case there is no black hole. Yes, in this case there is no black hole, but there is a non-trivial scalar field. So you can play with that later. Okay, so because we are in spherical symmetry and we need to add dynamics, so we need to include a scalar field. So we choose a massive scalar with mass parameter 1, so that's the mass term in the action of a scalar field, and we do a first order reduction. So the evolution, we say that it's like the Lie derivative along time without advection term is v, so that's what you need to multiply by the lapse. Okay, the Lie derivative along n, and we forget about the advection term. Yeah, I don't know why you forget about the advection term here. Anyway, and then that's the evolution equation for the scalar field. And then in the stress energy tensor, we need to compute the energy density of the scalar field, then the current, and the special part of the stress energy tensor. Those enter the BSSN equations. And finally, we get to the evolution of the right-hand side. So the right-hand side, yes, sorry, the advection terms are here. So, sorry, what I said is just rubbish. So that's the equation for the shift. Sorry, for the conformal factor, this equation. That's this equation for the conformal factor. Then that's the evolution equation for the metric, but now here we've already taken care of the factors of R, of the rescaling, so that's why we call it little h, right? The factors of R have already been taken care of analytically. This improves accuracy. Same thing for the evolution equation for the trace of the extrinsic curvature. That should be this equation here. That's this equation here. And likewise, that's the evolution equation for the traceless part of the eccentric curvature, again, with the factors of R taken care of analytically. Then the evolution equation for this variable, lambda, and that's it. Okay? And then we have a function here that computes the time derivatives. So when you do Runge-Kutta evolution, then basically we have for our variables, right? So for Runge-Kutta type of evolution, we have a vector of variables. Let's call it big U, which is a big function which will depend on these and the special derivatives. Okay, so these functions compute this vector. Okay, and that's a vector, and we align it in the same order as the variables. Okay, so we just have to put everything together. So the first thing that one does is we compute the determinant. So we know what this determinant should be, right? It should be just the determinant of the background metric. So by doing these redefinitions, basically we just make sure that basically any error of the determinant is taken care of. So we just rescale these evolved variables such that they satisfy that the determinant is what it should be. Okay, so in a way, this imposes by hand the constraint of the determinant. In the usual evolutions that we do in black hole binaries, we don't do that. Right? We just let it go and then you check that it is satisfied. Of course, this is satisfied everywhere except inside black holes, where anything, I mean, not anything can happen, but the constraints are not very well satisfied, but that's not a problem because that region is causally disconnected from the outside. So as long as that region stays well within the black hole, then is of no physical consequence. Okay? So, but sometimes this helps in improving stability. So that's why you do it here. So we just set to 0. So this is the vector of the right-hand side, and we'll split it into chunks. So we compute each chunk separately, and then we put them together. So first of all, we need the derivatives. So all variables appear with at least one special derivative. So we compute them. And then here we only compute the variables that need second derivatives. Right? And then here and we then compute the right-hand side at every point inside the grid without the ghost cells. Okay? So the ghost cells, the values of the ghost cells have been used here when you compute derivatives. Okay? But the right-hand sides are not evaluated at the ghost cells. Right? So we just do all the tensor algebra that we need, and then compute Ricci and so on and so forth, and then we fit in these functions that compute the right-hand side for each of the evolved variables. Okay? So this is the factor of 3/4 that we've seen today. These are the gamma driver and the 1+ clock slicing condition. And then we need finally the advection terms, which again, depending on the sign of the shift, then we use the information from the right or from the left to make sure that information propagates in the right direction. And that's given by the sign of the shift at that point. So we add the advection terms. Oh yeah, that's the advection term for the scalar field I forgot about. So we add the advection terms to all variables. And again, these factors that you see here is because we take care of the powers of R analytically. So that's why you pick up extra terms, but they just come from derivatives of the powers of R. You can just work this out analytically. And you can see we only do this for the points which are in the physical grid. And once we've done that, then we group all these into a single vector, which we call it right-hand side. And then once we have these, then we can use the standard RK4 type algorithm to step forward in time. We use Kreis-Oelinger dissipation, and we add this dissipation term to each of the variables. So that amounts to just taking like a suitable number of derivatives. So we add the dissipation, so we kill the high frequency noise in each of the variables. And finally, we fill in the ghost cells so that we preserve the boundary condition of the evolved variables. Okay? And that's it. So finally, once you have this, then you implement a simple RK4 routine, which I've done it here by hand. I'm sure there might be more efficient ways of doing it, but if you go to Wikipedia, that's RK4. And it can be for any equation. We've done it for BSSN, but it's basically it's a way to solve equations, first order equations of that form, whatever the right hand side might be, right? So that's a standard RK4 routine. And finally, we here as a diagnostic, we compute the Hamiltonian constraint. And this is something that in any numerical simulation, I could have also added the momentum constraint, but I just didn't do it, but I should have. So as part of any simulation, you should compute the constraints, because I said you that if you satisfy them initially, then they should continue to be satisfied to the future, but to check the correctness of your simulation and the accuracy of your simulation, you need to monitor the constraints as functions of time. So we compute them at every time step, for instance, or you need not compute them at every time step, but you need to keep track of them, and then you use them, for example, when you do convergence tests. So you know the constraints should converge to 0 if you solve the Einstein equations. So you want to, for example, solve the same problem at different resolutions and check and compute the norms of the constraints and check that they converge to 0 at the suitable rate, depending on your differencing scheme. In this case, we have a scheme which is 4th order in space and 4th order in time, so you should expect 4th order conversions. So if you have, say, 4th order in space and 2nd order in time, then you can only expect 2nd order in time. A global 2nd order conversions. But whatever you get depends on which errors are larger. So it could be that sometimes you're dominated by spatial errors, and then you will see 4th order conversions. But if you wait long enough, or if you then go to high enough resolutions, then eventually you will be dominated by the largest errors. In this case, it should be 4, but we don't have that. So here I'm not going to go through this. It's finished the simulation, so it doesn't take that long. So we coded up some tests just to where you compute geometric quantities, because again, when you write a code, the chances of making mistakes are basically 1. Okay, so one often writes tests that check certain computations where you know the answer, where you know an analytic. So for example, you can say, I've got, like, say, Schwarzschild. I know what the Ritchie tensor should be. So now I compute it numerically and compare with the analytic answer. And if my routine is correct, then fine. But if you've made a mistake, which is very likely to happen, then this is one way of detecting it. So usually when you do coding, a good amount of time is spending writing those tests and running those tests to check that the code is correct. Is that right, Shunhui?
I write the test for 2 months.
Exactly. Yeah. So you spend more time doing these boring things, which is not. Yeah, it's not a lot of fun, but it's necessary, right? Because I mean, after all, when you do numerics, you get numbers, right? And one of the most difficult things about doing numerics is to make sense of those numbers. And so you should not, I cannot emphasize enough the importance of doing these tests. Because otherwise you can just run simulation for months and it can be just complete nonsense, right? And you don't want that. So you want to make sure that you spend time efficiently. Okay, so the simulation has finished. So that's the initial data. We checked the Hamiltonian constraint initially. We've done the time evolution. And now we look at what the variables are in the final time step. So I think in the way I coded up this function is that here we are plotting these variables, but just changing these names, you can plot other variables, right? So let's plot conformal factor, the RR component of the metric, the lapse, this lambda variable, and the trace of the eccentric curvature. So if you plot that, then that's what you see. I just want to emphasize one point is that, first of all, nothing blows up, which is always a good thing. And notice that the lapse goes to 0 at the origin, as promised, for the 1 plus log slicing. So the lapse starting being 1. So in fact, this is interesting to look at that. So one can plot here the lapse as a function of time at different times. So initially the lapse, remember that time 0, which is not included here, was 1. And as time evolves, you see it collapses very, very quickly to nearly 0. So that's after only like time 3. So that's a very quick evolution. And then after that, not much happens, and the lapse is really pretty much pinned at 0. And the horizon, in this case, the black hole is a black hole of size 1, so the horizon is going to be somewhere around here, right? So all this region here is the interior of black holes. And you can see that the lapse in this region is very small, so coordinate time evolves very, very slowly here. So that's what we said earlier, that time is freezing inside black holes, but outside it does, whatever it needs to do, right? It's nearly 1 far away, so far from the black hole, time evolves at the rate that it should. Okay, one thing is that, as you can see, here the lapse collapses very, very quickly, almost exponentially fast, right? That's what these equations give you. Also the gamma driver is, you can show it converges exponentially fast to the desired coordinate condition. So that creates a problem. So usually, initially, you've got constraint violations from the fact that you are discretizing in space, but also because you have finite resolution in time, and you've got this very fast evolution. That's why initially you also have constraint violations from not having enough time resolution. And that comes from just gauge adjustment. So it's just gauge, right? Because our initial coordinates did not satisfy the 1 plus log slicing and gamma driver condition. So your coordinates will change, and that's not physical change, it's just coordinate evolution, but it's fast, and this generates constraint violations anyway. So that's what you see here. So here we can see, for example, here when it's plotting the lapse at a single point, and here it's at the point, it's not at the origin, so the first point in the grid would be number of ghosts plus 1. That's the first point in the physical grid. So we are plotting here at the second point. Okay, so that's R would be, let me see what value of R is, but it should be close to 0. See, that's near the origin, but not at the origin. Okay, and you see here at this point the lapse as a function of time and the extrinsic curvature. So you see this starts at 1, that's what we had initially, then all of a sudden, boom. There's very fast evolution, and then it just settles and nothing happens. So evolution freezes. And the extrinsic curvature, it does whatever it has to do. In fact, it goes to 0 here for I don't know why. So the other thing that we do is we check the Hamiltonian constraint. So what this function does, it will, in this case, one can compute the Hamiltonian constraint as part of your evolution. So something you can do is that, given the solution at a time slice, you can say, well, now I'm computing the Hamiltonian constraint. Or what this function does is that, since in this case is only 1D, so we can store all solutions at all times. So then we can just iterate over the solution to compute the Hamiltonian constraint a posteriori. That's something else we cannot do. And here, since we don't want to plot all of them, we'll plot the Hamiltonian constraint every 10 time steps. So otherwise, instead of a plot, you'll see like a spaghetti dish or something. So that's what this does, and that's barely visible. But basically, the point is that you can see that in the region far away from the black hole, then the Hamiltonian constraint is 0 and stays 0, as it should. But here near the origin, things, it's not as good. But again, this is because in these coordinates where your slices get pinned at that asymptotic region, you've got large gradients. So you will necessarily under-resolve those gradients. So you should expect large Hamiltonian constraint violations there. But as long as they stay outside the horizon, then it's fine. So that's it. So here's like some evolution. And we can do some oscillon evolution as well, if you like. Or I can show you the results. Yeah, I can show you the results because we are not going to have time for this. But basically, this is just a case of a space-time with a scalar field that back reacts on the geometry. And this, because the scalar field has mass, it will oscillate and eventually dissipate, because in flat space you cannot have stationary black hole with hair. So it will necessarily be time dependent, but it oscillates, but it dissipates on a very, very long time scale. So for a long time you see this oscillation. So that's what you see here. So these are the initial conditions. Then again, initial conditions satisfy the constraints, except at the origin. Then we evolve. This was slower or faster? Let's see. Yeah, this is going to be a bit slow. No, this is going to be the same. Anyway. Yeah, so that's what I was saying. So you see here, again, so that's the scalar field evaluated at the second point on the grid. So in this case, there is no black hole, but the geometry back reacts. Okay, so there is back reaction. And you can see that the scalar field oscillates. And it just, basically the amplitude of the oscillations is pretty much constant. But eventually it would, in this case, dissipate to infinity. But okay. That's why it's called oscillon, or oscillaton. And yeah, so that's the scalar field at different times. You can see that it oscillates up and down as time goes by, and you see the same profile. Okay. And again, the Hamiltonian constraint is a function of time. So here, because here the outer boundary is at 32 instead of 48. So it's closer, and you can see that's basically because we're not imposing the right boundary conditions. So you see some little bump there, that's error, that's unphysical. Oh, I even have an animation here. Well, anyway, so that will not run now. But basically what this would do is just oscillate up and down. Okay, and you can play with this. So I think that's pretty much it for today. Any questions about these numerics? But I just want to say that going from here to downloading GRChombo and running it is just is okay. So it depends on how familiar you are with like C++, but the structure of, I've written this mathematical code in the same way as GRChombo is written. So these different functions, they're just the same, right? So you can, if you like that something, it's perfectly doable. Okay, so going from here to running simulations in a cluster is a small step. So that's it. Any questions?
Is this code enough to, for example, model merge of the two black holes? So
This,
yeah.
Mathematica. No.
Like, okay, something like this. Or you need different approach, for example.
No. So the only difference in a black hole binary that this will not do is so for example, something that I've got one student looking at is this in ADS for single black holes. That's something which this would work very well. For binaries, spherical coordinates are not good, right? Because you've got the origin, which is visible, and with spherical coordinates, in this case, because you have only the radial direction, that's not a problem. But if you have the angular directions, then you can see that effectively your grid points near the origin, they cluster. So what determines the CFL factor is the smallest spacing, right? And in spherical coordinates, you get tiny spaces at the origin, and that is the limiting factor. So all the grid points cluster there, because the coordinates become singular, and then this forces you to take very small time steps, apart from the issues of having a coordinate singularity that you need to deal with. So this formulation is not good for black hole binaries. In that case, it's much better to use Cartesian coordinates, right? Because then you have no problem, and the spacing is the same everywhere. Okay, and then the other thing that the codes do that this obviously doesn't do, and you need for black hole binaries, is you use mesh refinement. So if you've got In a black hole binary, there are 3 relevant length scales that you need to resolve. One is the size of each of the black holes, so let's assume that they are equal mass, so same size. So the size of the horizon, that's one length scale. Second length scale you need to resolve is the orbital length scale, because the black holes orbit around each other, so you need to resolve that scale. And of course, that one can be 10 or 100 times larger than the size of each black hole. And then finally, you need to resolve the wave zone, right? Because you need to extract gravitational waves. So these 3 are widely separated length scales. And therefore, it would be madness to use the resolution that you need to resolve the black holes everywhere, right? Because that's clearly overkilling for the orbital scale and the wave zone. So what you do in practice is that you do this mesh refinement. So you've got a region with more points around the black holes, then fewer points in the orbital region, and even fewer points to resolve the wave zone. Okay, so that requires some infrastructure that is not here, and you need in practice in order to make these computations feasible. Okay, but this is to do with computing, it's not to do with formulations, mathematics, or physics. This is a computational problem now that we're talking about. Any other question?
Is time up?